Welcome back to Engineering Simplified. This video marks the start of the Robotics 201 video series. If you are new to this channel, in the previous video series, which was Robotics 101, we covered a lot of different concepts for 2D planar robots. And in this video series 201, we are going to cover the same concepts for spatial robots or 3D robots. So the first concept that we are going to start with is called a rotation matrix. So what is a rotation matrix? Allow me to explain. Let's say we have a fixed reference frame as drawn here, and we have a moving reference frame which is drawn in purple. And we can see that we can obtain the moving reference frame with respect to the fixed reference frame by a rotation about the z axis of an angle, let's say theta. So which means that this angle would become theta, and so would this angle be theta. Now let's say I have a point which is marked on my moving reference frame. And let's say that this point is 1 units in x, so its coordinates would be 1 units in x, 0 and 0 in y and z. And now the rotation matrix is a matrix which, when multiplied to this point, would give its coordinates in the fixed reference frame. Or mathematically speaking, if I call my point in the moving reference frame as small x, and the same point when expressed in the fixed reference frame as big X, so the A would be called my rotation matrix. So a rotation matrix times the point expressed in the moving reference frame would give me the same point expressed in the fixed reference frame. So I always denote everything in the fixed reference frame with capital letters and everything in moving reference frame with the small letters. So small x and capital X. Now, how do I figure out what my rotation matrix is? So let's say I have written out this equation again in a data expanded form. So my small x is 100 and my big X, just by simple trigonometry, I can see that it is 0 in z, and in x it is cosine of theta, and in y is sine of theta. Now, if you remember, for the 2D planar case, my rotation matrix was a 2 cross 2 matrix for planar case. Now for 3D case, it is a 3 cross 3 matrix for a spatial case. So how do I find the 3 cross 3 matrix? If I have a look at this, then I can see that something multiplied by 1 would plus something multiplied by 0 plus something multiplied by 0, which is the first row, should give me cosine of theta. So I know that this term, my 1 comma 1 term, the first term should be cosine of theta. And similarly, if I go about it, I get the following. So the first term has to be cosine of theta, the second term has to be sine of theta, and this term has to be 0. I don't know further what these 6 terms are, but I know that for sure that the first column is going to be these terms. Now let's say I extend this approach further and I mark a point on the y-axis, this one, which again is 1 unit in y, 0 in x, 0 in z. So it is 0, 1, 0. And now I follow the same process. So I write my rotation matrix 0, 1, 0, and I express this in terms of my fixed reference frame. And now, if you remember, I already know the first column, which is this one. So I already know this column, and now I have to find the remaining 6 terms. So I have rewritten my first column. Now moving forward, how do I determine the rest of the elements? So if I do a simple multiplication of the two matrices, so cosine of theta into 0 plus something into 1 plus something into 0 should give me minus sine of theta. So this term right here has to be minus sine of theta. And similarly, sine of theta times 0 plus something times 1 plus something times 0 should give me cosine of theta. So this term has to be cosine of theta. And similarly, this times 0 plus something times 1 plus something times 0 should give me 0. So this has to be 0. So I know these 6 terms now. The rest of the 3 terms are still remaining, but I know these 6 terms. And now I do the same for the z-axis. So I mark a point on the z-axis which is 1 units in z, so it is 0, 0, 1, and I go about doing the same process. And now I know that since the point lies on my rotation axis, it doesn't change. So its coordinate in the fixed frame is the same as its coordinate in the moving frame. And so if I go by the same approach, I get this. So now I have defined all the 9 terms of my 3 cross 3 rotation matrix. And this rotation matrix was about the z-axis, right? So what we call it is, we call this to be the z rotation matrix. So this 3 cross 3 matrix is known as the rotation matrix about z, or in short, z rotation matrix. And you may ask, do we have a rotation matrix about other axes too? Yes, we do. We have a rotation matrix about y, and we have a rotation matrix about x. And how do we figure that out? The methodology is pretty simple and similar. So, in order to construct a rotation matrix about x, what I like to do is I like to redraw my axis in such a way that x is pointing upwards, and this is my fixed axis. I draw a moving axis. So I draw a moving axis, so x has been rotated by an angle, right? And then I follow the very same approach as before, and I get this. So if the rotation is of an angle of phi, so I get this x rotation matrix. And very similarly for the y, I get this as my y rotation matrix. I would highly encourage you to pause this video and try to drive the x rotation matrix and y rotation matrix on your own. So now we have got the 3 rotation matrices: our x rotation matrix, our y rotation matrix, and our z rotation matrix, which is about the respective rotation axes. Now there are a couple of properties that need to be satisfied by a matrix in order to be called a rotation matrix. And what are those properties? It is these two properties right here. The first is that a rotation matrix times the transpose of a rotation matrix should be equal to the identity matrix. And if you know that an identity matrix for a 3 cross 3 matrix is this 1, 0, 0, 0, 1, 0, and 0, 0, 1. And the second property is the determinant of a rotation matrix must always be equal to 1. So if I need to check whether a matrix is a rotation matrix, I need to apply these two conditions, and if they are satisfied, then it is a rotation matrix. So now till this point we have covered what a rotation matrix is. For the spatial case, we have discussed the 3 different types of rotation matrices: the x rotation matrix, the y rotation matrix, and the z rotation matrix. And we have talked about these two conditions for a matrix to be classified as a rotation matrix. Now rewriting these again in a more compact form. So I have these. So my x rotation matrix is this, y is this, and z is this. And in place of any angles, I have just written a dot, since these can be any angles. Since this video is becoming a bit too long, I'm going to take a break here, and I am going to continue in the next video. See you there.